Now we have modified our table to have the measure and the confidence interval. So we can now go back here and paste this measure, copy this coefficient, and then we shall come back and copy the coefficient and its confidence interval. So remember that Stata doesn't put a 0 in front. So you got to put it yourself. And if you are going to do 2 decimal points, all you're going to round this off is almost going to become 1. Okay, because it's 9999. But let me leave it there and keep those. And then add in bracket the confidence intervals, which I've indicated here. And so you go back here and copy your confidence intervals. And once you copy the confidence intervals, you paste them in your table. Right there, you paste the confidence intervals. And we can avoid those things getting screwed up a bit by making this table a bit more beautiful. We beautify the tables. And then we add the zeros in front for our viewers to see the 0 point. And then we can decide to maybe stop at 3. And if I didn't want actually, I didn't want to round that one off to 1, but if we leave it there, now that is the coefficient. So now the coefficient has confidence interval. That one is minus. So we now go back and get the coefficient for the second one. And of course, you are going to have to interpret them. We are going to come back to the interpretation. So just in case you are saying, oh, I don't know how to interpret them, then the question is going to be, did you actually do Biostat 2? Because if you did Biostat 2, then you should know how to interpret this, and that's why we insist that it should be a prerequisite. Okay, so we now put in the confidence intervals. We stopped at 3 decimal points, so we do the same, put a 0, 3 decimal points, it will round up to 6, it will round this 5 to 6. Okay, now there we are. You can use a hyphen and say this 2, like this, or you can use a comma, depending on the journal. Some people see that one better, which has a hyphen. Now, the issue that comes up here is interpretation. How do you interpret this? Because this is now a model that has one coefficient, one independent variable in it, and one dependent variable. And let us now switch to the blackboard and see what we have here. Let us switch to the blackboard and see what we have. In this model, we have, so the current model is birth weight in kilograms. So we have what we call the expected birth weight in kilograms is equal to the beta naught or alpha, the intercept, plus beta 1 times age in what? In categories. Okay? So beta 1 is a dummy variable because it has more categories. So this is going to give us 2 coefficients. It's going to give us a coefficient beta 1 comparing 1 to 0, and it's going to give us beta 1 that is comparing 1 versus 0, and also going to give us another beta for beta 1 that is comparing 2 versus 0. Now, if you look in that table, the minus 0.09999 is this one. The other one is positive 0.09999. 205.251, something of the sort. And the intercept, beta naught, is 2.97 something. Now recall from linear regression. Now all these things still come back. From linear regression, the intercept here, beta naught, is the expected birth weight in the kilograms when the age is what? When this variable here is 0. And what is this variable when it is 0? What is coded 0 for this variable is 14 to 19. So the average weight of a baby born to a mother aged 14 to 19 when this category is 0 is 2.97 grams. Don't just interpret these things mathematically and say 2.97 is the intercept. So what? What does the intercept? It is the value of y when the x here is 0. And when is x is 0, this variable is for those aged 14 to 19. So the average weight or expected weight of a baby born to a mother who is 14 to 19 is 2.97 kilograms before we adjust for any factor. Now, compared, now here we are comparing. Those, what is category 1 is 20 to 29. When you compare category 1 of 20 to 29 versus category 0, what do you find? That on average, the babies born to mothers who are 20 to 29 years are almost 1 kilogram less than the comparative group. Whereas, because this is a minus, whereas those born to mothers who are 30 to 45 on average weigh 0.2 kilograms heavier than the reference, which is 14 to 19. But this is crude, it is unadjusted. Then when you go back to the table, to Stata, we look at something else on Stata, and the table gives us the t value, the p, and the confidence interval. We see that none of these p values for these two is less than 0.05, so there is no statistically significant difference between these categories. And we see also the confidence intervals here include the value of 0. Because remember, it's not only 1 or 0, but it's the value under the null hypothesis. Okay, now we can also do that for age as a continuous variable, not for age as a categorical. So we come and say regress. We regress this with age. With the age. Okay, there we are. And now we have a coefficient which is a positive 0.012. And we have the coefficient. Now the model changes. Let's go back to the blackboard. Now the model is changing. Now this model is now reads like that the expected birth weight in the kilograms, baby birth weight in the kilograms, is equal to the intercept times beta 1 plus beta 1 times age. So when does this model reduce, this side reduce to only beta naught? It reduces to beta naught when the age is what? 0. You see that? So when the age is 0, and here I want to teach a very important concept. When the age is 0, this model reduces to expected baby weight in the kilograms is equal to beta naught plus beta 1 times 0. Any number times 0 is what? 0, which is equal to, so this model becomes only beta naught. Okay? So now, beta naught there is 2.6 what? 2.65 something. Now, how do you mathematically interpret this? This is, remember now we are modeling age as a continuous variable, which means every year change in age is associated with some change. But now, this would mean that this is the expected what? Age, expected weight of a baby born to a mother whose age is what? Whose age is 0, because this is now continuous. This is not categorical. But do you expect a baby, a mother who is 0 years to give birth to a baby? So this is where now biology and science comes in, because these models and numbers, they're playing around with what? With the numbers. So does this intercept make a sense? Absolutely not. Because a baby, a mother aged 0 years cannot have a baby themselves, because at 0 years, they are still what? Babies, okay? So how do we make the intercepts meaningful when we are dealing with the continuous variables? We make intercepts meaningful when we are dealing with the continuous variables by using what we call centering of variables, continuous variables. And we only center continuous variables. Continuous variables. And what does this mean, centering continuous variables? So, for example, our minimum age, the very minimum is what? Is 14. So we have this variable here, age, and we have them starting from 14, going all the way down to 45, okay? Now we want to make the intercept meaningful by using age as a continuous variable. So we generate a new variable known as age centered, or age center. And this age center is going to be equal to age minus 14. The lowest, we set a variable according to its lowest value, age minus 14, and that is age centered. So where our typical age is 14, so this is age, it is 14. What will be the value for age centered for a person aged 14? Here it will be what? 0. If this person is 15, what will age center be? It will be 1, because it is age minus the lowest value. After we've done we sorted the value and described it. So the person who is 20, age center will be what? Will be 6. The person who is 45, age center will be what? 31. So now, age center makes sense. Why? Because if age center is 0, we know that mother will be aged what? 14. Okay? So we now go back to our data set and generate a new variable. So generate age underscore center is equal to this original age minus 14. Okay? Then we bring that variable where all the ages are. So we say order ID 2. Remember that hyphen 2, age cut. Immediately after that, follow it with age center, so that all the age variables are in one place. Then we label the variable. Label var age center, and we label it age minus 14. And you realize that I use age minus 14. I'm not actually using age hyphen 14, because I want the variable name to be fully meaningful to me. because age dash 14. If I use the dash, it may mean just dash. But here I want to be sure it is minus. So now I can browse these variables. Age, first of all, let me first sort them. Sort age, so that it is in ascending order. Then I can browse age and age center to be sure that where it is 14, the other one is 0. Where it is 15, the other one is 1. You see? Now I can visualize. So I know now my computer did what I told it to do. Now I set this model again, and I set grace. First of all, what should we have put in the do file before we center this variable? We generated a new variable. And so we should have come here and put, annotate, centering age by the lowest value of 14. Okay? Then we do, we created a new variable, age center is underscore. Age center equals to age minus 14. Then we bring that command that did it. Where did we do that? Here. So we highlight that command and we copy it and actually paste it there. Okay? And we save. Then we go back and do this model again. And we say regress. But now instead of using age, we are going to use age what? Age center. And there we go. Now, do you realize that it is making sense? So we now have a coefficient. We now have a coefficient. If you go back to the board now, we have a coefficient. After we've centered, we've now fit the model based on the centered value. So we have expected birth weight in kilograms is equal to beta naught plus beta 1 age center. And we get the values. Beta naught is 2.83. This is equal to 2.83 plus what is the coefficient is 0.012. 0.012. So what does this mean? This means that when this thing here is equal to 0, when is it equal to 0? When the mother is aged 14 years. So this intercept now makes sense. So the average weight of a baby born to a 14-year-old mother is 2.83 kilograms. Note the mathematical that the average weight born when age is equal to 0. Because now we have to apply science. Okay? So we've now made this intercept meaningful by centering this what? Variable. And this one doesn't change. It still remains a year difference. So it means that if two mothers differ in age by 1 year, the older mother will on average have a baby who weighs 0.12 kilograms more than the younger what? Mother. Now, when it is like this, it may not look much meaningful. But when you turn this into grams, it will be 12 what? Grams. For every year difference in the age of mothers, the baby born to an old mother weighs 12 grams more than that born to a younger mother. And this is still unadjusted. So now, we can now start to put in, so this is the crude. Now we can now go and do the adjusted model. So now you do this for all the variables in your crude or your table. you do all the unadjusted and you put their confidence intervals and interpret them. Now I'm skipping it to the adjusted because this is a review. So now we are putting a variable. We are putting expected body weight. Body weight is already in kilograms, is equal to beta naught plus beta 1 age center plus beta 2, what are we going to put in beta 2? Race plus beta 3, we are going to put in mother's weight at conception plus beta 4 hypertension plus beta 5 uterine irritability and so on. Okay? Now we are doing what? An adjusted model. So you can put in here adjusted linear regression. So now we go back here. We have some, and we are using the xi because we have some variables that are 3 categories, although you can actually do that in the new modeling without necessarily having to put there the xi. Then we also put smoke. We put, let me put smoke, hypertension, uterine irritability. Let me just put those. But of course we also put mother's weight. And so they are missing smoke. Now, so I add, in my model, smoke was number 3, number 2 actually. So beta 2 smoke, and so beta 2 is smoke, beta 3 is hypertension, HT, beta 4 is uterine irritability, beta 5 is mother's weight at last menstrual period, which is LWT. Now, once you do this, let us interpret these variables. What does beta 1, beta naught stand for? Beta naught is when all these ones are what? 0. Okay? So you got to go back and look at how these variables were coded. Do you expect a mother to have had 0 weight? Eh? We don't. But we know that non-smoker is 0. No hypertension is 0. No uterine irritability is 0. But so the expected weight of a baby whose mother is 14 years, because we centered this, non-smoker, no hypertension, no uterine irritability, weight at last menstrual period was 0. Makes sense? No. How can a mother have a menstrual period when she's weighing 0 kilograms? So what do we mean to do? We need to center that variable as well. So we go back and say, summarize low WT in detail. Summarize low WT in detail. So that it gives us the lowest, and the lowest is what? Is 80 what? Pounds, not kilograms. So if we want to convert this into what is meaningful to us, we first change this variable to what? To kilograms. And say generate low birth weight in underscore kg is equal to low birth weight divided by 2.2, because there are 2.2 pounds in every kilogram. Then, as it takes place, order these variables so that the ones that are related are near each other. Everything from ID to the low birth weight to weight, and then this in kilograms. Now, once you bring them there, then label the variable. Label var LT, even though it shows here LWT, again, you may say, oh, I see the kilograms. Please still label it. Weight weight in kilograms at last normal menstrual period. Fine. Now we go back and now summarize the new variable, which is in kilograms. Summarize this in detail. So what is the lowest? Kilograms, 36. This was a teenager that became pregnant. 36 point what? 0.66, okay. So this is the lowest. So we are going to go and center it. And now say, generate low birth weight in kilograms. We can even say C for center is equal to this low birth weight minus what? The figure I copied there from the lowest. Okay? Then I order. These things appear easy here during the demonstration, but my friend, people get problems with them all the time. So I need these variables all to be seated together so it becomes easier for me to see them. Then I label this variable. Label var as weight in kg at last normal menstrual period centered at 36.36, something of the sort, centered variable. Now the next thing we browse to see, does this, but before we browse, we first sort. So we sort this weight in kilograms. Then we browse this weight in kilograms together with the centered one. You see? Now there is a problem. Some of the weights were not the lowest. You see? Because this would have been 0. Do you see that? This would have been what? 0, but it is not what? 0. So that means we have a problem. So now we drop this variable that we generated. And now we sort this one again, and we browse that variable. $36.364. Now, how come? What did we center with? With exactly the same. Why didn't you do it then? It created some extra decimals. They are not showing up. So what do we do to make it, to leave it what? Okay, let us center it in pounds. Let us center it in pounds, where it is more clear. The lowest was 80, wasn't it? Okay, so let us center it in pounds. We are now going to drop it in kilograms and summarize it in pounds. 80. Yes. Here. 80. So we center it in pounds. And we say generate LT center is equal to LWT minus what? Minus 80. Okay. Now we order this variable to LWT, and we've centered it. So we browse these two variables. We need to label it, but we browse them to see if it did the same thing. Now we are okay. Now we are absolutely okay. We now do our model again. Now I'm not going to go through label details because now you know what it is. So now we do our model again, but this time instead of putting in LWT, we put LWT centered. So if we come back here, we put LWT center, and we centered around 80 what? Pounds. Remember that? Okay. So now what does beta naught mean? Beta naught is the expected baby's birth weight for a mother whose age is what? 14 years, because this has to come 0, non-smoker, doesn't have hypertension, doesn't have irritability, and whose weight at last menstrual period was 80 pounds. So please, please learn to know how to make a meaningful analysis. Don't be fooled by numbers, because the program will give you numbers regardless of what. And now, we can now know that the intercept for here is the expected difference between the two mothers whose age differs by 1 year. The expected difference in babies born to two mothers whose age differ by 1 year. If we hold smoking constant, hypertension, irritability, and what? And weight at the last menstrual period. So you can say beta 1 is minus 0.004, okay? So minus 0.01, but remember this one now has got what is in the model. It has the age center, okay? You now see that for two mothers whose age differs by 1 year, the expected baby's weight decreases by 0.0047 kilograms. After we've adjusted for race, smoke, hypertension, uterine irritability, and mother's weight at what? At, you see that? Yeah, at last menstrual period. But you see now that age is not a significant thing, age center. Look at this p-value, 0.612. But race is, you see that? 0.01, 0.0. Smoking status is. Hypertension is. Uterine irritability is. Weight of mother at last menstrual period also is. So now, when you are doing your modeling, this is why you should have set your standard, that I will leave in more variables that are predictors of this whatever, that's of this outcome. They are statistically significant at this p-value. So if you set that, then in this case we are going to drop what? Age, because it is not age center. So we fit in a model and we remove age center because it is not a significant predictor. Now you bring back all your bio 2. You see? Now the story changes. We only keep those that are significant, statistically significant, and the coefficients change. But the other thing is that you can keep or many variables that are not statistically significant. Why? Because they are biologically important to be adjusted for. You don't just drop every variable because it's not statistically significant. No. Some you can leave them there even though they are not statistically significant, but they are biologically important. But you should have determined that in your analysis plan. So we're going to take a break and now do the same analysis using logistic regression where the outcome is categorical. Thank you.